Electricity in our world has always used resistance. The filament of a light resists the flow of electricity and becomes white hot. The element of an electric kettle becomes hot because of electrical resistance. Resistance appeared to be a law, but in 1911, Kamerlingh Onnes used liquid helium to cool mercury to about 450 degrees below 0 Fahrenheit. Suddenly, the mercury lost all resistance. Onnes had discovered perpetual electrical motion, superconductivity. At temperatures approaching absolute 0, a current will flow forever in a superconducting loop. Without resistance, huge currents can be transmitted. If the temperature is kept cold enough, those currents will generate immense magnetic fields which can do work. Today, we know how to handle the super cold liquids that make superconductivity possible. We even ship them around the universe because rockets use super cold liquid hydrogen for fuel. Using super cold liquids, we can begin to build the first practical superconducting machines. This tiny tube carries liquid helium to supercool the rotor of a superconducting generator. The tube must be a tiny steel-walled vacuum bottle, like your thermos, but it must be far more effective to work at 450 degrees below 0. This conventional magnet uses 5 million watts of electricity to produce a huge magnetic field 500,000 times as strong as the Earth's. Its electrical resistance is so high, it needs 800 gallons of water a minute to keep it from exploding. A superconducting magnet, just as powerful, draws only a small amount of power for cooling. Pollution of the air and water, the threat to our life-sustaining resources, must be overcome. Smog-choked skylines can be seen and felt in the nose and throat and lungs. Rivers in urban areas are still safe to sail over, but deadly to swim in, and deadlier still to drink. Superconductors may be the answer. Almost everything is attracted by a big enough magnetic field. Even pollutants can be separated from water with superconducting magnets. Dr. Henry Cohn of MIT.
They're now designing a magnetic filtration unit which will take all the coliform bacteria and suspended solids out of this water and make it clear again. And this is possible only because superconductivity makes it feasible to generate magnetic fields that are needed to do this. Without superconductivity, it would be completely out of the question. I can demonstrate that for you at the lab. Now, we have here a demonstration that shows you the effectiveness of a high field in separating very finely divided colloidal material. And the first separation we're going to try is just some iron oxide, finely divided and mixed with aluminum oxide.
The huge magnetic field generated by superconductors magnetizes a steel wool-like mesh in the separator. Almost everything is attracted by the force. One substance can be separated from another by the difference in the attraction. Even bacteria can be removed by seeding the water with a little iron oxide. The process is hundreds of times as fast as ordinary filtration.
This beaker contains scrubbing water obtained by cleaning the flue gases from an oxygen furnace. It presents a major pollution problem because the particles in it are too finely divided to be removed by filtration, and somehow one has to get rid of the water. Now let's see what magnetic filtration will do to this problem. We put this material through the same magnetic filter, and notice it goes through it just about as fast as you can pour it out of that beaker. And the water coming through at the bottom is clear. It is in fact drinkable.
A full-scale separator mounted on a barge will soon be removing pollutants and leaving clean water behind. Someday, superconducting separators may even remove pollutants from fuels before we burn them. The low-field room in the bitter magnetic laboratory at MIT. The steel capsule may look like a moonship, but it is in fact very necessary. It It is made of a special metal which conducts magnetic lines of force. Even the magnetic field of the Earth is deflected around the space within the capsule. In this room, almost free from magnetic force, is a superconducting magnet which can measure the minuscule magnetic fields produced by electric currents flowing in the body. Brainwaves, heartbeats, messages down the nerves can be measured more precisely than ever before. The room has even been used to map deposits in the lungs of asbestos miners from Quebec. The story of superconductivity's power to realize the dreams of science fiction continues here. Engineer Bruce Montgomery of MIT.
That's fine. We're looking at a catheter, which is a small hollow silastic tube, which we are going to introduce into the vessels in the brain. It must be very soft in order to introduce it into those vessels because they're extremely tortuous. And it is too soft to push, as one does with catheters going into the heart, for example. So we have developed, with Mass General Hospital, a magnetic technique for pulling the catheter. You may turn on the field. You can see that the magnetic field attracts the tip of the catheter, on which we put a small permanent magnet. And by rotating this magnet around the head, I can essentially draw the catheter through the vessels in the brain. The reason that we wish to enter the brain in this fashion is that we can enter this tube through a small incision in the neck and reach deep into the brain in areas that otherwise would require extremely dangerous open skull surgery. This is not a superconducting magnet, but it is strong enough to attract the catheter if I am close enough to it, allowing us to work near the edge of the head. But deep within the head, the magnetic fields are so weak that we can no longer act effectively on the tip. To allow us to work deep within the brain, we're building a superconducting magnet, which will have actually 10 times the magnetic field of this device, and yet it fits in an extremely compact package. To try to do this job without superconductors, using conventional technology, would have required an enormous power supply and a magnet weighing many tons, which would not be sensible to use in the operating room at all.
This technique is so simple that some operations may be done by radiologists. The tiny catheter, dancing its way through the bloodstream to the tune of a superconducting magnet, will be used to strengthen damaged blood vessels and even to cut off the flow of blood to cancers. Development of superconductors, our target impossible, can do even more for us outside our bodies. The energy crisis. Cities that once blazed with light look darker now. Sometimes they are browned out and even blacked out. Despite the fact that we are frantically building nuclear power stations, we still need to burn coal and oil to generate power. Superconductivity offers us a new way to use fossil fuels that will give us 50% more of the energy released by combustion. The secret is the high temperature, close to that of a rocket engine. Temperatures of 3,000 to 5,000 degrees Fahrenheit are necessary for real efficiency. Here at the Avco Everett Research Laboratory, they're working on a system that has been called the greatest advance in combustion since Prometheus gave man fire. Magnetohydrodynamics, or MHD. Dr. Arthur Kantrowitz.
We're sitting here in the middle of a MHD generator, which gives us a particularly good opportunity to understand how this generator works. It starts here with a combustion chamber, much like a rocket combustion chamber, heavily water-cooled. that puts out a very high temperature stream of gases, just as a rocket does. These gases pass through a magnetic field. It goes like this, that you have a conducting medium flowing across magnetic field lines. And the magnetic field lines are horizontal. The flow is horizontal in the other direction, and the electricity is generated in the vertical direction. There is a channel. That channel picks off the electricity in just the same way as the brushes of a generator pick off the electricity that's generated by copper moving through a magnetic field. In this case, it's a high-temperature gas. The magnet here is made in the conventional technology of making copper magnets. That is, the current flows through copper. It will be replaced in about 18 months with a superconducting magnet, which we are now building. And that magnet will have much stronger magnetic fields and enable us to generate more electricity.
Immense magnetic fields can literally extract electricity directly from a rocket's blast. Because of the incredible temperatures, MHD will produce 50% more power than conventional techniques, with virtually no air pollution. Only superconducting magnets make it feasible to draw power directly from a rocket blast. Many scientists believe that thermonuclear fusion, the power source of the sun, will be the ultimate solution to our energy crisis. The sun's enormous gravity compresses the gas plasma and heats it to incredible temperatures, and atoms fuse. On Earth, we can produce fusion, but we cannot control it as yet. H-bomb explosions are uncontained fusion reactions. Before we will control fusion on Earth, we must learn to contain it in reactors like this one at the Bitter Magnetics Lab at MIT. Engineer Bruce Montgomery.
To make a thermonuclear fusion reactor work, you must heat the plasma to 100 million degrees. And to do so, you need very high magnetic fields to compress the gas, keep it away from the walls. And to create those very intense magnetic fields, we have a magnet here that's the highest magnetic field device of its type in the world. And to get that kind of magnetic fields, we require ultra-low temperatures. And the frost you see through the window on the outside of the magnet indicates that it is at present at 200 degrees below zero. The future of such devices requires that we must go to even lower temperatures and use superconductors.
Fusion on the sun is patterned and controlled by gravity, as these computer displays testify. On Earth, superconducting magnets will exert enough force to tame the raging energy of fusion. A full-scale reactor 10 times this size couldn't generate enough power to run its own magnet. Superconductors could do the job running on flashlight batteries. Speed, rapid transportation from one bit of world to another, has been the dominant drive of 20th century man. But our holy quest for speed is bogging down. Airports are becoming saturated. Faster, bigger planes need too much land for runways. Kennedy Airport uses 7.5 square miles. Toronto International uses 25. Kennedy's 7.5 square miles of land is enough for a 95-foot right-of-way from Boston to Washington. Transportation planners have dropped their eyes from the skies to the land, but trains are limited to between 130 and 150 miles per hour. Most tracks aren't even smooth at walking speeds, so alternatives must be found. The most promising alternative uses superconductors to produce repulsive magnetic levitation. Called the magneplane, it is being developed by Dr. Henry Kolm of MIT.
This magnet is neither attracted nor repelled by aluminum. However, if the aluminum is moving, as such as we can simulate by making this wheel spin, the magnet will be repelled by the aluminum because it induces eddy currents, and these eddy currents oppose the penetration of magnetic flux into the aluminum. And the faster the wheel spins, the stronger is this force. Now notice that contrary to attractive maglev, repulsive maglev is inherently stable. You get a feeling for what this force is like. In fact, repulsive maglev has certain similarity to aerodynamic flight, and here at MIT we like to think of it as electromagnetic flight. We're producing lift at the expense of drag due to the motion of the magnet with respect to the aluminum, exactly the way an airplane wing produces lift at the expense of drag by moving through the air. Now we can demonstrate repulsive magnetic levitation even without motion. And to do this, let's take an ordinary coil of copper wire into which we can feed alternating current, which makes the magnetic field generated by this coil vary rapidly. And now, above this aluminum plate, we can produce levitation simply by allowing this coil to float. Now, in this case, we make the magnetic field change instead of moving the magnet over the plate. And this, again, will give you a feeling for the inherent stability of magnetic levitation or electromagnetic flight.
Ordinary magnets couldn't feasibly levitate something as big as an airplane. Only superconductors could do that. This superconducting chassis will ultimately fly the 1/25th scale model magneplane. The track is simply an aluminum trough with propulsion windings. These windings travel back and forth in meanders. Effectively, the magneplane is like the rotor of an ordinary synchronous motor, except that it travels along the track instead of turning. A clearance of 12 inches will make it possible for the magneplane to fly at 300 miles per hour. In a partial vacuum, it will be possible to go faster than modern jet transports.
2, 1, go!
This is film of the first successful public demonstration of this type of electromagnetic flight. The magneplane's first payload was our camera, so you are the first passenger on what may be the rapid transportation of the future. Superconductors carry electricity without any resistance. This new force will give us superconducting magnets that will do enormous amounts of work and do it virtually for free. Electromagnetic flight will be a full-scale reality in a decade. In the 80s, MHD will use superconductors to extract power directly from a rocket blast. Superconductors will deliver electricity from H-bomb-like fusion in 20 years. This year, superconducting catheters will be used in knifeless surgery. With support, scientists will give us the superconducting devices capable of lengthening our lives and conserving our resources. Soon we may reach our impossible target and turn energy into limitless force.